Hello everyone. Let us start with session 3 of week 7, wherein we are trying to understand NCCL, all reduce, and multinode in terms of distributed training. So let's try to understand why doesn't the communication blow up as the number of GPUs grow. That effectively tries to answer the question as to if the number of GPUs grow, okay, how do we ensure, okay, that the communication between the GPUs is not a bottleneck for the increase in the throughput. Okay, so for example, there are ways of trying to reduce the traffic. So if you understand the concept of all reduce, as in case of MPI, which we were discussing earlier, there are two approaches. One is called as the naive all reduce and ring all reduce, the thing which NCCL does. Here, in case of naive all reduce, what effectively happens is that every GPU sends its gradient to every other GPU, right? So if there are n GPUs and the gradient size is m bytes, okay? So the per GPU traffic is big O of n star m, right? And if you double the GPUs, you basically double per GPU communication. This effectively means that if you try to scale yourself up to 8 GPUs, the traffic is so much humongous that the advantage of trying to use GPUs is almost gone. And then you have this approach of ring all reduce, wherein the GPUs are arranged in a logical ring, right? It's basically topological thing, okay, wherein each GPU only talks to its two neighbors, and the per GPU traffic now here reduces to 2 star n minus 1 by n star m, right? And if you go on increasing the number of GPUs to infinity, basically, the traffic, okay, tends to move to 2m. So it is independent of n. So it's very useful, right? Even if you scale the number of GPUs to whatever number you like, and the traffic is just double the size of gradient size, whatever gradient value is, it's just the double of it because you're trying to communicate with only your two neighbors, right? So this basically is a very good approach to understand and save the bandwidth required for the processing, right? So the win here is per GPU bandwidth is independent of the cluster size if we are trying to talk about ring all reduce. So training 8 GPUs, if you're using 8 GPUs, right, and use it for training, it costs the same communication per GPU if you are trying to use 1024 GPUs for training, right? So the basic idea stays here is that the algorithmic foundation of scaling to thousands of GPUs is maintained using this particular formula, right? And we are independent of the number of GPUs we use. The traffic is basically hovering around somewhere 2m, right? So now the algorithm, just to have a brief idea of what ring all reduce algorithm is, we split the gradient into n chunks. So we know that the gradients are being calculated, right? So we split the gradient into n chunks, and there are two phases, right? Each taking n minus 1 steps. Basically, it starts with 0, ends with n minus 1. Okay, so number of chunks are n. So there are two things which we do. One is reduce, scatter, then all gather, right? So in case of reduce scatter, what we do is each GPU sends the chunk mod n to its right neighbor. Neighbor sums the incoming chunk with its own. After n minus 1 steps, each GPU holds one fully summed chunk. So the basic idea here is we are trying to actually send okay, chunks using this rank k mod n. So if it is step k, that means the chunk size of rank k mod n is sent to its right neighbor. Okay, so one GPU will have its right neighbor and left neighbor. So it will receive the information from left and then do everything and send it to right. So the neighbor sums the incoming chunk with its own, and so on and so forth. After n minus 1 steps, each GPU holds one fully summed chunk, right? And all gather phase is the second phase wherein each GPU passes its fully summed chunk around the ring. So there are n minus 1 hops, each receives the other n minus 1 chunk. After n minus 1 more steps, every GPU has the full sum. It basically goes through all the hops and reaches the same GPU. So this is how basically it's going to happen. Okay, and this is this ring all reduced. So you try to collect the sums as easily as possible just by your neighbors and then go on passing it, and it basically travels in a ring like fashion. Okay, so the NCCL, which we are talking about, which basically is the thing which we basically use, okay, and then this is a topology aware implementation, right? This is basically by NVIDIA, and this basically means that when you are trying to communicate, right? So there are two types of communications. One is the intra-node communication, and one is the inter-node communication. So when I'm talking of intra-node communication, I'm talking of, let us say, the communication which happens between all the 8 GPUs which are there on the DGX server. Okay, that's a single node. Okay, considered a single node with 8 GPUs, and there we use NVLink, we have NVSwitch, and then there is PCI Express P2P, wherein you are talking about direct GPU to GPU or PCI Express bus, not over the NVLink communication medium. So this PCI Express P2P is a possibility when you have a different box, okay, which does not use NVLink, which uses PCI Express bus for, let us say, 2 GPUs or 4 GPUs on a HP system or a Dell system, okay, which basically again has multi GPU thing, but which does not have NVLink, right? So that is the intra-node communication methodology or a method when you want to connect 2 GPUs over PCI Express, right? And NVLink is basically inside the DGX server, and there you get about 900 GB per second on the H100, right? And NV switch, basically, if you have got a lot of H100 boxes, then you want to connect all of those, then you can use NV switch. Okay, and then if you are using PCI Express, this is about nearly 50 GB per second, right? The other buses, right? Direct GPU, PCI Express bus. Internode, you need to have InfiniBand plus GPU direct, wherein zero copy GPU NIC is the best. You have ROCEV2 plus GPU direct. You have this remote direct memory access over the Ethernet, and then there is the socket programming of TCP, okay, and which is basically slower. But the basic idea is you have got these types of communications which you need to use, okay, in efforts to basically use multi GPU system or distributed training systems, okay, for training your models. So this is the way in which basically the NCCL is used. So at the initialization, basically NCCL probes the visible devices. It actually reads the NVML topology, discovers the NICs. It builds a graph of which GPU share NVLink, right? And which of them basically use the PCI Express route, and how are the NICs which are closer to the GPUs, then picks the fastest string and then goes on, no, basically coming, rotating around all the GPUs in the circular fashion, basically ring like fashion, right? So when you want to use this PyTorch distributed communication layer, which is called as C10D, it is basically a multi-node rendezvous with collective communications, basically. So if there are n independent processes across k machines, right, how do they find each other? So what basically happens is this is a multi-node rendezvous with collective communication. So till now we were trying to see, we were working on a single GPU. Okay, then we saw how basically we can run our programs on single node multi GPU systems. Here we are talking of multi node systems, right? So here we are talking of process basically starts by knowing its own rank, total world size, a master address port, right? And then you basically have to have a ring topology. The training starts peer-to-peer communicators between all the ranks, and then you have this TCP store, okay, to connect, and then you will have to use telnet and number the nodes uniquely, right? And then try to link those nodes specifically, and PyTorch actually gives you that type of API. And then there is this communication layer which is C10D. Okay, not going into the details again, but this is what basically the NCCL debug, socket name, Ethernet port, which Ethernet interface basically we use, okay, and how do you force the TCP fallback. So all of those things, right, of how do we use NCCL environment variables basically which you use, and the bandwidth basically the interconnect things which you should understand. So the latest thing is NVLink 5, which is on B200, and it's intranode thing which you use, which gives you a speed of about 1.8 terabytes per second. And then you have this NV switch, which is all-to-all communication in the XGX type of environment. It gives you about 900 GB per second. And then internode InfiniBand NDR somewhere around 400 to 800 GB. Then PCI Express, if you see, you get about 64 GB per second. And TCP socket, right, you get about 10 to 25 GBs per second. Okay, so this is how basically the bandwidth actually varies when you shift from NVLink to the TCP socket, or when you go down to PCI Express P2P type of bus. Okay, so this basically means that the NVLink is a proprietary communication link which is very very optimized for the bandwidth which it gives. Okay, when you are trying to work on intranode, and then you should use NV switch for the best um, communication, which is basically all to all, and then InfiniBand NDR basically for internode communications, right? So this is how basically distributed training is generally more dependent on the communication media, the infrastructure which is required, okay, and which actually effectively gives us the throughput and the bandwidth, okay. So to summarize, NCCL is a topology aware thing, right? We talk about NVLink, NV switch, in the bandwidth ladder, okay, and we can debug the rendezvous with telnet, master address port, so on and so forth, right? So this basically gives us a sense of how these communication things work at the lower level, okay, of the whole infrastructure network, basically giving us this required speed and required effective training time getting reduced because of this infrastructure and the bandwidth and the technology underneath. Okay, so this is the end of session 3, and we'll start with the next session 4 in the next class. Thank you.